Hello all, welcome back to this interesting series which is going on machine learning fundamentals. We are on a very interesting topic. We discussed in fact cross validation in the previous episode, and this is in fact the continuation of that. It is episode 13 itself, but it will be the second part of that, and we are going to discuss a few more very critical and important aspects. I'll be just going and presenting some of them, and then I'll be taking a consolidated holistic program, a very simple one on which we had earlier given some examples. It is related to medical diagnosis, and we will be taking these all these aspects into consideration there, and we will see how the results vary when you're taking different parameters into consideration, and how those results are getting impacted and influenced by those, and that will be showcasing the critical aspect and criticality of these different aspects which are very important in fact. For somebody who is into machine learning, applying that into a realistic scenario, a use case, a critical use case, it's imperative, in fact, to consider these, and definitely go for these aspects, and put them as appropriate to that particular situation and a program. So without any further delay, I will just display first of all the presentation. We are going to hyperparameters. We discussed cross validation last time, and then hyperparameters. What is this? Why guess parameters when you can search systematically? So definitely there is we are having in fact some mechanism which will be telling us that we what combination we'll be having. So in this one we are given an example. There is definitely an analogy. You can just find it with the recipe or cooking. When you can have in fact a cooking in fact is two aspects are there in cooking. So that analogy you can just fit to this so that you can understand what this is. When we are we are finding the optimal settings for the model. What this is. When we are cooking, there are two very important aspects. One is the ingredients which are there, so which by which you are preparing a particular dish, and then one more is in fact the recipe. So ingredients is one thing in the recipe. So it needs an exact amount of things to put in, so that you will be getting that optimal taste. So that will happen only if the recipe is proper, and second thing, the ingredients which you're using, they are proper. So that is I think a best analogy which fits to this situation as well, and that is the example that has been given here. If you just see, uh, you don't need to guess. Grid search tests all combinations, random search samples efficiently. You can think of it like a cooking data is ingredients, algorithm is, so data is ingredients for this, and algorithm is recipe. So you can just see that data, it is calling ingredients, and then the algorithm is the recipe. Hyperparameters are the settings. So when we are talking about hyperparameters, these are the settings. So in which aspect you have to put ingredients, and for how much of time you will be cooking, what will be the way you will be you'll be cooking a particular dish. So that is going to make a difference. So that is exactly what hyperparameters are doing on a particular in a particular situation in a model. So if you just see this analogy, the cooking metaphor which is there, grid search is like trying every possible combination of oven temperature. So it will be trying everything, every temperature at which it will be cooking a particular dish, and cooking time to find the perfect recipe for the dish. So it will be finding the perfect recipe for the dish. That means those parameters which are there. It will be finding best parameters that are suiting your machine learning model. So this analogy fits it well. So hyperparameter tuning. So what are those key parameters, for example, for random forest? So hyperparameters tuning, if we have to do in random forest, what aspects we need to keep in consideration? We have discussed them off late as well. One is N estimators, that is number of trees. So that is definitely impacting. We have discussed it earlier as well in the previous episode. Maximum tree depth, that is one more very important aspect which will be impacting. And then sample split, maximum minimum samples, and then max features, the features, features at each split. I think these are these parameters which are given here. This is a little repetitive, that I'm repeating this again here. I have discussed this in the earlier series as well. But connecting this with the grid search is something, that's why that has been repeated here. So grid search implementation will be exactly telling us the combination of hyperparameters that you should be giving for a particular machine learning algorithm, making in fact our job much easier. So it combines hyperparameter tuning with cross validation. We have discussed cross validation in this particular episode itself in the first part. Define a parameter grid, then let sklearn systematically test all combinations to find the optimal settings. So what this grid search is actually, GridSearchCV is doing for us, it will be giving us the exact parameters with cross validation, and then we'll be able to find the optimum settings that we can go for a particular machine learning algorithm. And I'm going to showcase to you this with a very exhaustive, detailed example implementing this with Python. Interpreting a grid search. So this is something which is there, understanding your best model. Grid search systematically tests parameter combinations, and reports the optimal configuration. So it is giving you the optimal configuration that is suiting the your model, best model. So best accuracy of 0.96 indicates strong model performance. So max depth, for example, 6, and estimators 200. That means number of trees. Minimum samples split 2 optimal, and best accuracy 96%. So this is an example which it is giving. For example, a grid search is providing you and then giving you what is the optimal solution for your optimal parameters for your model. And then there is one important thing which we have discussed to some extent as well in the previous episodes, that is bias variance trade-off. So what is this? Bias means a model is too simple. When we were discussing, in fact, we have discussed it in quite a detail, in fact, underfitting and overfitting. So when we are talking about bias means model is too simple and misses important patterns. And variance means model is too complicated and it overfits, and it adds unnecessary noise which is complicating the model, and it is adding the noise which is in fact that is creating a problem, or that will be degrading or decreasing the accuracy by adding the noise in the training data. So these are two things, bias and variance. And bias variance in model types. So comparing decision trees and random forest, for example. Decision trees have, so if we just see the factor of bias, bias and variance in two models, for example decision trees and the random forest, you will just see and observe that decision trees are having low bias but high variance. So what does that mean? They fit training data well, but are sensitive to small changes. So that we have in fact highlighted this particular aspect when we were discussing the decision trees as well. Random forest reduces variance by averaging multiple trees, achieves better generalization. So random forest, on the other hand, that is achieving better generalization. That is what actually is the motto behind. So when we are looking at a good fit model, best fit model, we are looking at this factor, one aspect, that what is the capability, competence of generalizing. So model should be having actually a capability of achieving this better generalization. That's what happens with random forest, because it reduces variance by averaging. So that is there. And the feature selection, why it matters, we have discussed it earlier as well. If you are having a good feature it is going to improve your accuracy. It is going to improve your accuracy, and at the same time, if you are having a bad feature, it will be adding unnecessary overhead. It will be adding unnecessary noise, and that is going to reduce your accuracy, while the good features improve prediction and they reduce complexity. So bad feature and a good feature, so you should be actually taking optimal features. And if you remember, we had discussed while discussing random forest that it's having an inbuilt capability, so that is discussed here. In fact, random forest provides built-in features for importance scores. So we have in fact done it in previous 2-3 programs which were related to random forest, that we have displayed which are those features which are significant ones, very important ones, and how much how much of the decision or the portion of that was, how much impact this particular feature had on this on the deciding of this particular result. So that also we are displaying there. So this is important scores ranking which features contributed to most to the predictions which are there, as I was telling you. This helps identify the most valuable input for your model. There might be certain features might be there which will be very insignificant, or they will be just increasing the complexity rather than contributing in a positive manner. So there is this code which in fact I'm going to showcase to you in a much elaborate or detailed manner. So I'll be showcasing you directly the VS Code. So feature importance, you can have 10 ranking that we have already done. Worst perimeter, mean concave points, and then worst radius. This is something which we had taken actually in the earlier episodes. Before discussing this, in fact, ROC, I will be just taking the maybe the model at the Python implementation at the end, because it includes all of these things. I have just put a single Python program with the previous example itself to make it very simple for the viewers, that all of these concepts which are there, whether we are talking about hyperparameter, variance, and bias, whether we are talking about this ROC and AOC, all of these things. So these all these features, or hyperparameter, all of that, bias and variance, and this grid search in fact, and then so that is also there. So grid search also we are using in this same program, and then hyperparameters and key parameters to tune. All of these have been taken into a single program, a very simple program, and it will be displaying and using all of these things. Let us just go to this ROC curve. What is this ROC? Intuition and purpose. Visualize the trade-off between sensitivity and specificity. What is this? So ROC is receiver operating characteristic. So what is this receiver operating characteristic? It is a curve. So curve plot, the true positive values which are the true positive rate against the false positive rate. There's a curve plot which is between true positive rate against the false positive rate across all classification thresholds. So this helps us to evaluate classifier performance beyond a single accuracy number. So it is giving us, ROC is giving us actually an idea of how this true positive rate is has been segregated, and how it is in against with the false positive rate. In certain implementations, I would say ROC AUC is very critical, because we want to just get how many true positives and false negatives were there. So that is something that particular ROC will be giving us a better understanding, rather than having a overall accuracy number, which in certain cases I would say, for example, that doesn't work. For example, fraud detection, it is ROC is very important in very critical in such an implementation. So this is giving us exact idea, apart from the single accuracy which is there. So this particular thing you have to remember, ROC curve implementation. So this is the implementation code which is there, which we are going to use. In fact, we are using sklearn and matplotlib to visualize the trade-off between the true positive rate and false positive rate. So this is a trade-off between true positive rate and false positive rate across different classification thresholds. So definitely it is giving us a trade-off between the two. And then what is AUC scores? AUC score is area under the curve. That is, is an area under the ROC curve, and what it measures is how well a model can distinguish between classes, how well a model is distinguishing between positive and negative classes. So if a model has a good distinction, that means AOC value will be higher. Something, for example, near to 1 will be considered as an excellent, good fit, best fit model. If it's having an AOC, that means it is separating positive and negative classes in a very well manner. There are values, in fact, I am showcasing those values to you. These are the values. If it is, for example, 0.5, it is random guessing, so there is no skill, in fact. So nothing has happened. You can just say, so that means machine learning model is not, giving an optimum, it's not performing well. 0.7 to 0.8 is a good performance. We can consider this as a good performance. 0.8 to 0.9 is very good performance. And something which is 0.9 plus is an excellent classifier. If we are having values less than 0.5, that is considered to be it is useless, because it is worse than random guessing then. So that is there. So these scores, AUC scores, very critical. ROC, AUC, values very critical for certain implementations. So this integrated pipeline will be the discussion which we'll be doing later, but I will be showcasing you these things which we are having. They will be displayed on your screen now. This is a program, in fact, which I have I have written this for these various aspects: hyperparameter, variance, ROC, AOC, and it is taking into consideration all of these. Let me just give a simple brief explanation of this program. This is very simple. We have taken most of the things already. I'll just tell you what this is. First of all, importing of different things which we are using here. So that is something which is a norm. And again, then we are having load data set. So data set we are loading. We are loading that breast cancer. If you remember, we were doing a medical diagnosis on breast cancer. So same program it is. There are few of the modifications which are there, which are related to these different aspects, so that they will be highlighted. That is the only thing. Otherwise, the program is same. We are using the same program. So we are loading the data set, and then we are printing the this data. So data frames, and then target names. So X and Y. Target classes and data features, data set features. And then we are train test split we are doing, as we said, 25 and 75%. Test size is 25. And then random state is same, 42. So X and Y. And then we are going for bias variance demonstration. How do you do that? So underfitting model, high bias, we are using decision tree classifier for this. And then we are saying that depth is 1 and random state 42. For a good fit, we are taking depth as 4 and random state as 42. This particular thing we had done earlier as well. So I'm quite confident you will be aware about this program. We have done it before. Our fitting model, high variance, decision tree classifier, again, we are taking here. And we are giving depth none. That means it can take unlimited. And then random state is 42. That will be giving us, high variance. It will overfit. So then we are putting this bias variance demonstration here and printing these different, values. You can just see by putting a loop, for loop, name model in a model.items, model.fit is equal to X train, Y train. So this will be printing these, if you just see, for loop is running on this, and it will be printing training accuracy and this train accuracy and round train underscore ACC. So training accuracy and testing accuracy will be printed. So then after that we are having a parameter grid, max depth, minimum sample split, and then minimum samples leaf. So base model now we are taking as decision tree classifier, which we are changing, and we are giving one aspect here, that is random state is equal to 42, so that our results are consistent. And then we are putting this grid search, which is something new we are doing. That is the only thing which we are doing new. So that is a grid search. So grid underscore search is equal to grid search, and then we are opening it up. Estimators is equal to base model, and parameter grid is equal to parameter grids, and then CV is equal to 5. So we are putting it here 5, and scoring is equal to accuracy. And then we are so scoring of this will be equivalent to the accuracy which it will be achieving. Okay, and then in fact we are printing these parameters. So best parameter grid search dot best para. So these all values we are getting from the from here itself, from sklearn itself. So all of these values, if you just see, they are coming from sklearn. And then we are having in fact the this is best, okay, test results. No, we were here. So best parameters, cross validation accuracy, so that also we are printing. And then we are putting in fact the best model grid search best estimator, so that also we are getting from sklearn itself. Test accuracy, accuracy score, x test and y test. And then we are putting then that best model test result is the one test accuracy, round test accuracy 4. So we are putting the best, printing the value of that. And then y underscore probe, and in fact these values we are putting inside these variables, and then we are making them to print AOC score and ROC results. So we are printing them, and after that we are plotting a graph, in fact which will be a curve, ROC curve. So that curve will be giving us in fact an idea that how much you can just say how much curve is there, and how much differences between the classes, how the program has, or the model has segregated positive and negative classes with a curve. It will be giving us the idea about that. So this is what this ROC curve for tuning decision tree. And then we are getting this we are showing plot.show, and it will be showcasing us the curve, so that we get an idea about how much difference is there between the positive and negative classes. So this is a program. In fact, in between, just one thing we have added new is this, which is talking about the grid search. So this particular code is new. Rest everything we have done it before. So if you just see this grid search, which is here, starting from here, so this grid search is new. You can just see hyperparameter tuning using grid search. So we are doing this particular mostly this one. So this particular thing which is highlighted here, this is something new which we are doing for the first time. Otherwise the rest of the things we have done it before as well, multiple programs. So here we are giving parameter grids, in fact new values, and then we are using as we said that in ingredients of a particular dish, and then after that the recipe. So these we are modifying so that we'll be getting. So this is what is hyperparameter tuning. This can happen in different aspects. This can happen in parameter grid which is there, so that we have discussed in theory as well. So that those values we are modifying here, and then we are getting optimal results from there. So if you just see, I will be running this program, and maybe I will just pull it up a little bit. Yeah, I can pull it up, and then you can just see. First of all, it is printing the data set which we are giving x and y, and showing what are the target classes. In fact, target classes are malignant or benign. So we are talking about the classification of that, cancer, this one. It will be giving us that. First of all, it is saying that bias variance demonstration, underfitting model, high bias. So training accuracy is 0.922, testing accuracy is 0.92. Again, this is underfit, which is almost coming as similar, not much of a difference. But good fit model is the one where training accuracy is 0.98, and testing accuracy is 0.94. And then there is in fact overfitting, where the training accuracy is 1.0, and then testing accuracy is much lesser. It is coming to in fact similar to underfitting model. So that means it is overfitting there. So you might be having in fact different values, what we are getting here, because this is just a test thing. So if it is a realistic situation, when we are comparing, underfitting, good fit, and overfitting. It might be having significant differences which are in fact critical. As I told you last time as well, it doesn't matter how much of a difference is there, but differences can sometimes be, they can be catastrophic to a particular use case, and that will be making a huge impact and difference. So that's why we need to have a good fit model. So we don't want an underfitting or overfitting. So both the things we have to avoid, and we need a good fitting model. It can have huge impact in a particular use case. So this is just a test which is going around here. Grid search results, best parameters. So it is showing what are the best parameters which are there. So best cross validation accuracy, and best parameters which are there: max depth, minimum sample leaf, and minimum sample split. So this 5, 2, and 5, it is giving these best parameters which are there. So grid search is telling you best cross validation accuracy is 0.9413. Best model test results is test accuracy is 0.94. ROC, AOC results, if you just see, AOC score is near to 1. I won't say it is 1, but anything which is above 90 is excellent. So it is falling in that particular category. And if you see the ROC curve as well, you can just see there's a huge margin, and it segregates the positive and negative classes quite evidently. So that's it. So if you just see interpretation of these results and all of these things, we have done it practically. In case you are having any issues whatsoever, because it can well happen, I'm trying to give an explanation of the code in the best possible manner, but sometimes it may happen that you might be having some doubt somewhere. So in that case, what we can do is that code which is there, for example, this is a very simple code which is there for a grid search. So that is starting from here. So step 4, if it is there, this one, I will be providing, in fact, maybe a kind of a definition, more definition to this, line by line as well. Or you can just search for this particular thing, and for the further studies, you can just see this. This is very simple. I'll be putting an explanation in the comment section. You can go to that and see the definition of each of the lines which are there. I have given you already the commentary of each of these, but if you want further, for examples, in somebody's mind this is not clear, rest of the things we are taking we have taken them in the previous episodes as well. So I don't think there should be any problem in those, but maybe this particular step 4, hyperparameter tuning, you might need a little bit of a more exposure to explaining these lines one by one, that I'll be putting on the comment section. Thank you so much once again for in fact joining this very important features, hyperparameter, AOC, ROC, and bias and variance. We have implemented this practically. We have seen it, seen the different definitions. Please provide your valuable feedback so that we can improve this, this particular channel, and especially related to machine learning fundamentals. We are currently running this particular series, so we can improve this series for the benefit of the viewers. Thank you so much once again for joining, and please subscribe to the channel if you feel that this is beneficial in one way or the other for you, and provide your critical comment so that we can make it better. Thank you once again for joining.